So today we're going to talk about quantum error correction, abbreviated as QEC or QECC. QEC stands for quantum error correction, and QECC, if you have one more C, means that quantum error correction code. So also in the classical computer, you need a code to make an error correction. So you're not just storing the information of bits into your device. So you're kind of coding your bit information into some kind of other types of bits so that you can easily find out. Not always, I'm not saying the error correction success, error correction happens all the time. So I'm saying that if you have encoded 3 bits into 5 bits, then you have a higher chance to get correction. But if you just store 3 bits into 3 bits, then you don't know how to correct, right? So that's how basically the error correction works in the classical computer. But in the quantum computer, it's working differently. So in quantum error correction, it's actually error detection rather error correcting. Because how are you going to find out that error is occurred? Because you have a quantum state, which is superposed state. You have no idea how coefficient of ket 0 and ket 1s are. And if you take a measurement, you make a collapse, you kind of collapse your quantum state into ket 0 and ket 1. So the quantum error correction, the whole idea is stay the original quantum state intact. So you don't want to do anything on your data qubit. You don't want to do any change on your data, but figure out if any error has occurred in the state. That's the whole idea. So here we have to focus on error here. So in the classical computer, every information is bits. So it's either 0 becomes 1 or 1 becomes 0. So there is only one type of error which is not gate. So if you have unwanted, so if you have an error, it means in the classical computer, it means that you have unwanted X gate or X operation happened in your memory, right? So X means not. But in the quantum error, so if you want to classify all the quantum errors, there are infinitely many, because anything that changes the original quantum state is an error, right? But you have to take the final result. Our final stage of every quantum circuit is measuring the quantum state. So it's either happens to be 0 or 1, right? So of course there is a case when you're supposed to measure 0, but it turns out to be 1. So that means your final stage, your final quantum state was 0 ket, but it somehow error occurred, so it turns into ket 1. So in that case, we say it's X error, which means that unwanted NOT gate has been occurred to that quantum state. So there is an X error. And there is one more thing besides X error, which is called the Z error, because if you see the quantum state, I didn't mention about the Bloch sphere, but the quantum state is a superposition of ket 0 and ket 1. So even there are phase difference between ket 0 and ket 1. So this phase could undergo an error. So instead of, let's say, plus ket, let's say 0 ket and 1 ket is superposed with the coefficient 1 over square root of 2. But if it undergoes the phase error, then the phase difference, so in the plus ket state, there's no phase difference. So the angle between this ket 0 and ket 1 is 0. But if it has a phase error, then the phase difference becomes pi degree difference. So it becomes plus ket minus ket. So plus ket 0 minus ket 1. So there's another type of error in a quantum error. So this is called bit flip error, and this is called phase flip. So in more general, we call it decoherence. So anything that quantum states are contaminated, which means that it changes its state, is called decoherence. And I'm not saying that every decoherence is categorized into these two. So these two are the most extreme case, and mostly it's not exactly X error or Z error, because it's not that every quantum state, let's say bit flip error is like this quantum state turns into this, because it's somehow changing alpha and beta, but the effect of altering this coefficient alpha and beta, we say it's X error if the resulting quantum state are measured, and then measured outcome is similar to what happens when I apply the X gate on the original quantum state. So this is the perfect X error, so it kind of a bit flip error, but I'm not saying that this is always the case, that this is the only case that we can get a quantum error. So we're just kind of pushing all the types of errors into two categories, as if this is the only case, but we don't know. I mean, nobody knows what really happens, but just we are hoping that we can fit that error into two categories. So phase error, phase flip, by the way, is when you have this quantum state, then this is alpha 0 minus beta 1. Okay. So bit flip error, you can detect it by taking a measurement, right? Because let's say if you have alpha 1 and beta 0, then it becomes ket 1 here, right? So we can easily see that it's happened. But phase flip, well, you can see directly by measurement, because it only changes the sign. So the probability, the measurement outcome, will be the same thing as before. But when you have the phase flip error, and you say, let's say you have another gates in your circuit, and then you want to proceed your quantum algorithm, and somehow the phase flip error will at the end turn out to be giving the different result than expected. So these two are also equally important. And yeah, so this is the kind of a bit flip and phase flip error. So let's think about the simplest quantum error correction I can give you. So here is circuit. So anyway, so let's. I'll give you the example, and then I'll define what that is. Okay. So let's say we have two qubits, and we organize our quantum circuit like this, and let's see what happens at the end. So I'm going to take a measurement on here. Okay, C. So let's see, this one is 0, this one is 1, this one is 2, this one is 3. So psi 0 is 0, 0. So And then let's see. I'm gonna put this quantum state as a right-hand side here. So when I take under Hadamard gate here, so we get 0 plus, right, at the first stage. And after taking, so if I expand this, this is 0, 0 plus 0, 1. So after having a CNOT gate, this 0, 1, it becomes 1, 1, right? So we have entangled state. And what happens at the end? We have psi 3. So now we undergo Hadamard gate again. So we have 1 over square root of 2, 0 plus 1 over square root of 2, 1 minus. So if I expand this, I get 1 over 2, 0, 0, plus 0, 1, plus 1, 0, minus 1, 1. So at the end, I'm going to measure this qubit. So I'm going to combine according to the right-hand part. So we get 0, 0 on these two states. So we get 1 over square root of 2, 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 0. And then the combined rest other parts, we have 0, 1 minus 1 over square root of 2, 1, 1. And let's see, so we have 1 over square root of 2, 1 over square root of 2, 0 plus 1 over square root of 2, 1, and take a tensor product for the first time. So this is the quantum state I get after taking a measurement and see the 0 as a measurement outcome, right? So this is the plus ket state. And then this one is 1 over square root of 2, 0 minus 1 over square root of 2, 1 times 1. Okay, so if C was 0, then, so I'm going to call it the name for these two quantum qubits. So this, the first one is a measurement qubit, and the second one is data qubit. Okay, so, and the data qubit is at the state, data qubit is collapsed into plus ket, right? Plus ket. So if C is 1, then it collapses into minus, right? So, and you also have to be careful, make an emphasis that if your data qubit, so after running through this, after taking a measurement, you kind of change the data qubit state because it was originally ket 0, but now it's either ket plus or ket minus. So ket plus is eigenstate of the X gate. What do you mean by eigenstate? It means that it preserves the same state, only differed by coefficient. So what happens? Let's see what happens when I apply X gate to the plus ket state. So we have X 1 over square root of 2, 0, 1 over square root of 2, 1. So it becomes 1 over square root of 2, 1 plus 1 over square root of 2, 0, right? So it's a plus ket state. And you can see that this plus ket is a plus 1 eigenstate. So eigenvalue of this eigenstate is plus 1. And what about minus ket? We have minus ket, then this is minus of minus ket. You can see, you can do the similar calculation here. So this is plus 1 eigenstate of X, and this is minus 1 eigenstate of X. Okay, so this is extremely important. This concept is extremely important. And we can do the similar thing with Z gate instead of X gate. But before we move on to that, I want to emphasize what will happen if I run this circuit again with the same states. So, which means that, okay, so I need to, let's see, just initialize my data qubit here. Okay, so let's see. Since I take a measurement, it's, let's say C is 0, then automatically my measurement qubit is collapsed into ket 0 state. So my ket 0 state is here, and my data qubit is collapsed into plus ket state. Let's see what happens if I run this circuit again. So you can imagine that this is a continuous state, continuous circuit to the right here, the original circuit here. So let's draw the circuit first. And 0, 1, 2, 3. And let's take a measurement at the end. So psi 0 is what? 0 plus. I think I put the 0 on the right, so it's plus 0, right? And psi 1. So let's expand this. 0, 0 plus 1, 1, 1, 0, right? So now there's no so the control qubit is always 0 in this case, right? So there's nothing happens at the psi 1, so it's the same as psi 0. And then what is psi 2? So psi 2 changes the measurement qubit, so 0 becomes plus, so square root of 2, 0 plus, plus 1 plus, right? And no, it's just 1. Oh, sorry. So this is 1. I made a mistake here. So this is 1, 2, and this is 3. Okay. So let's expand psi 3 a little bit more. We have 1 over square root of 2. There's something going weird here. So, oh, okay. So I think I made a mistake here in the beginning here. So it's plus plus, right? So it's plus plus. Yeah. So yeah. So that the original statement is right. Psi 0 was plus 0, but I kind of skipped one step. So let me modify a little bit here. So psi 1 is applying Hadamard to 0. So here we have plus plus. So it's going to be sum of 4, right? Sum of 4 states. So 1 over 2, 1, 1, and 0, 1, right? And then, yeah, so psi 2 is not same as psi 1. So what we have is, so in these two cases, you changes the bits, right? So we have 1 over 2, 0, 0, 1, 0. And here it's 0, 1, and here we have 1, 1, right? So actually it's the same thing, right? It turns out to be the same thing, but it's not automatic. So what is psi 3? So here we again apply Hadamard on the measurement qubit. So we have 0 plus, 1 plus, 0 minus, 1 minus. So there are going to be 8 symbols, but there's going to be some canceling out. Let's expand everything here. It's a 2 square root of 2, 0, 0, 0, 1, 1, 0, and 1, 1, and 0, 0. So up to this far, I got this 4 thing here, plus. And for the minus part, we have 0, 0, minus 0, 1, and 1, 0, minus 1, 1. So here is canceling out, and here is canceling out. So these two, there are 2 of those. So we have 1 over square root of 2, 0, 0, plus 1, 0. So let's make it into a tensor product. So it's 1 over square root of 2, 0, plus 1, tensor 0. So this is the data qubit, quantum state of data qubit. And this is the measurement qubit. So what did I tell you? So we have already collapsed our data qubit into plus one eigenstate of x. It was plus ket, right? And because we took a measurement and measurement outcome was 0, the measurement qubit was collapsed into ket 0. If I run the circuit again, the same circuit again, then I don't change anything. So the data qubit is already, still plus ket state, and the measurement will be still 0. So that's something that we have to remember here. So whenever you have stabilized your data qubit into eigenstate of x, then it stays the same as long as there's no error. Okay, as long as there's something going on. If everything goes perfectly, because just assuming that there's nothing wrong here. So anyway, so let's think about other case. So this is about x measurement, and we can do the same thing with the z measurement. So h, and we have c naught, it's not c naught, it's a controlled z here. And we're gonna take a measurement here. So let's see what happens if I do this. So psi 0 is 0, 0. Psi 1, let's say psi 1 is 0 plus, and psi 2 psi 2, I think I should expand this a little bit. 1 over square root of 2, 0, 0, plus 0, 1, right? So it changes this part. It should change this part because there's only 1 here. So, but Z gate doesn't change anything here, right? So it's just same thing, psi 1. So, and then what is psi 3? Psi 3, you apply Hadamard on the measurement qubit, 0 and 1 here. So it's 1 over square root of 2, 0 plus, plus 0 minus, right? Now let's expand this. So 1 over 2, 0, 0, 0, 1, 0, 0, minus 0, 1. And because we're taking a measurement on the measurement qubit, let's combine these two. And so actually it's canceling out, right? Nothing to combine. So we have just 0, 0. Actually, it's not a good example. Sorry. So it's already given as it's already given as the eigenstate. So we get 0, 0. Nothing changed. So let's do it. Let's do it another thing here. Let me do it this way. So in the X case, in the X measurement X case, I decided whether the initial state of the two qubits are either 0 or plus. I can do the same thing here. So I put 0 here and plus ket here and see what happens. But it doesn't have to be either 0 or plus or minus. It can be any quantum state. So let's say we have psi state. Let's say psi is just random quantum state here, and then see what happens after taking a measurement. Okay, so I'm gonna do the same thing. So 0, 1, 2, 3. So psi 0 is just psi tensor 0. So it's alpha 0, 0, beta 1, 0. right? So psi 1, now we apply Hadamard on the measurement qubit, alpha 0 plus, beta 1 plus. Okay, so let's expand this a little bit. 1 over square root of 2, alpha 0, 0, alpha 0, 1, and beta 1, 0, beta 1, 1. Now let's apply the control Z. Psi 2, when do you apply control Z? The only thing you change is this part, right? So this part, you apply Z, but that doesn't do anything on the cat 0. So here it's changing the sign. So this becomes 1 over square root of 2, alpha 0, 0, alpha 0, 1, beta 1, 0, minus beta 1, 1. So now let's go to the third stage. Psi 3 is 1 over square root of 2. And Hadamard on the measurement qubit. So it's alpha 0 plus, alpha 0 minus, beta 1 plus, beta 1 minus. Okay, so let's expand this. So we have 1 over 2, alpha 0, 0, alpha 0, 1, alpha 0, 0, minus alpha 0, 1, up to this far. So we have beta 1, 0, beta 1, 1, and minus beta 1, 0, and plus beta 1, 1. Right? So there's some canceling out. So we have these two canceled out and these two canceled out, right? So let's see, there are two of those. We get what? Alpha 0, 0 plus beta 1, 1. So which means that alpha 0 tensor 0 plus beta 1 tensor 1. Okay, so that's right before taking a measurement. So we are taking a measurement here. So that's the measurement qubit. So suppose that we have C equals to 0. So measurement outcome was 0. Our data qubit is stabilized or collapsed into what? Cat 0, right? So when C equals to 1, then the data qubit is stabilized to 1, right? So we have psi. So data qubit collapse into 0, and if C equals to 1, then all things collapsed into 1. And you can see that 0 and 1s are eigenstates of Z gate, right? 0 is the plus 1 eigenstate of Z. 1 cat is the minus 1 eigenstate of Z. So everything works the same way. So if you run this again, let's say you measured the data measurement qubit and reads 0, so data qubit is collapsed into 0. And let's suppose that we undergo the same circuit again. What happened? You make the data qubit and the measurement qubit stays the same state. Nothing changed, right? So now interesting going on. So what we have done is kind of initialization process of quantum error correction. So again, quantum error correction is a code. It's kind of algorithm. So you need to encode your quantum state or quantum information into a code consisting of larger number of qubits, and then you want to initialize them so that you can transfer your quantum information into some quantum state of your code, and then you can now detect whether there is an error or not. So let's say we have plus cat here. So let's see what happens when I apply that gate here. What is it? Minus, right? So this means that Z gate changes +1 eigenstate of X into -1 eigenstate. Right? So, and also let's see that minus cat. What is it? It's a plus cat, right? So these two equality equation shows that whenever you have applied the Z gate onto any of eigenstate of X, it changes into another eigenstate. So it's, if it was +1, then it changes minus. If it was minus, then it changes to plus, right? So it's kind of flipping between the eigenvalue of the eigenstate, but still the eigenstate, but just the eigenvalues is different. And also let's look at these two equations. I mean, kind of obvious equation that we learned in the beginning, but I just want to emphasize because this is the most important part. Actually the core idea of the error correction. Every error correction, I would say, every type of error correction, quantum error correction, depends on these two facts. So if you have these two, then you can see that the same thing is true, that if you change your Z into X, then you change X into Z here, then same thing holds. So X gate changes to +1 eigenstate into Z of Z into -+1 eigenstate. All right. So how do you detect the error now? How do you detect error? So suppose that you have some quantum state and you had some read-off of your measurement qubit. Now I give it a name. So this is called the measurement qubit. And this is called the data qubit. And here we have, let's say, X. So because we have a X naught here, a controlled X gate here, we can call it X measurement qubit, or sometimes called X stabilizer. And now suppose that we have unwanted Z error here. So having Z error means that we have somehow magically the Z gate appeared in our circuit, right? It's same as having Z error is actually same as applying Z gate, but that's an error, so it's not our intention. So anyway, applied here. So if psi was the, let's say if psi was the +1 eigenstate of X gate or X, then because of Z, what happens? So it changes the eigenstate into, eigenvalues into different one. So because of this unwanted Z gate, this +1 eigenstate turns into -1 eigenstate of X. But then if this was -1 eigenstate, what happens to the read-off? It changes to 1. So originally it was +1 eigenstate. So if there was no Z error here, the read-off must be the same 0. But because of Z, it changed the eigenstate, +1 eigenstate into -1 eigenstate, so the read-off must be changed to 1. So let's try to compute this. So what happens after the measurement? So here it's 0, and here is 1, here is 2, here is 3. So let's assume that this is plus, which is +1 eigenstate of X. So let's see. Let's just verify if what I said is actually true. So we have psi 0 equals to +0 and psi 1. Now apply Z gate here. We have minus, no, not minus, yeah, minus, right? And 0 is plus now. And then let's expand this. Actually it's 2, and let's see, 0, 0, minus 1, 0, plus 0, 1, plus minus 1, 1, right? So now let's apply the C0 gate. So here and here, it applies to x. So we have 1 over 2, 0, 0, minus 1, 0, and 1, 1, minus 0, 1. So no canceling, but we're going to apply Hadamard again. Psi 3 is 1 over 2, 0 plus, 1 plus, 1 minus, 0 minus, right? So let's expand this. So we have 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, minus 1, 1, 0, 0, plus 0, 1. So there must be some canceling here. 0, 0, 0, 0 canceled out, and 1, 0 canceled out, and there are 2 of each here, right? So we get 1 over square root of 2, 0, 1, minus 1, 1. So this is minus tensor 1, right? So you have only one measurement outcome. You can always measure 1. So instead of 0, if there was no Z error here, it would be 0. But because there was Z gate, so the measurement outcome of your measurement qubit was changed to 1. And also your quantum state is, of course, changed to minus ket. So here. So we don't, so the key part, the important part is we're not measuring the data qubit. So this is the data qubit. We are not measuring this. We're not measuring this. We kind of know by computation that it's changed its eigenstate. The eigenvalue is changed. How do I know that? I know that, I don't even know whether this set is occurred or not, because I just mentioned that it's supposed that there is set gate, but in real life, I don't know whether there is set or not. So the only way, this is my point. I want to know whether this is actually here or not. So only way I can see the existence of that Z gate is this measurement outcome. So this is the measurement qubit, and we measure this. And because we measured different outcome, it was originally 0, but now it changed it to 1. So we know that the data qubit of this circuit is now undergo the Z error because it changed its eigenstate. So we kind of know that there must be Z error. So we just detected X error, Z error here, right? That's the everything. We just detected. We're not correcting it. We are detecting it. Well, you could have corrected because after the measurement, well, still this data qubit is there. We didn't measure it, so it's not collapsed. So because, after measuring this measurement qubit, since the output is changed, we can assume that there is that error. So we can kind of putting the Z gate on the circuit on this data qubit to correct it. But in real quantum computer, the quantum state lasts very, very short times. So that's one of the problem of making a quantum computer and why it's so hard to make a quantum computer. So quantum state only lasts for not even millisecond. So it's what's smaller than somewhat smaller unit than millimeter. So millisecond, nanosecond maybe. So It's very, very short time. So if you want to run the quantum circuit, then you have to set your quantum circuit all the way up to the end, right? So you cannot just change the circuit on the fly because it will just change. I mean, the whole information is just vaporized, no meaning at all if you do this. So, so let's say this. So this is actually nothing to do with this data qubits here. So suppose that I want to just preserve the data qubits. Okay, so I have the first plus ket state, and then I want to see whether the plus ket state is the same plus ket state after some circuits, after some times running this circuit. So you run the circuit, and then you're kind of detecting every time you finish this one cycle, and then you take a record of what the measurement outcome was. And then let's see, this is your final result. So here we have X measurement outcome, and here is your cycle. Let's say cycle 0 is your initial stage. So measurement outcome was 0. So you kind of know that this is plus 1 eigenstate in this case. So your data qubit is initialized as plus 1 eigenstate. And let's say we took another cycle of this quantum circuit again, and then the measurement outcome changed to 1. So now you can imagine that this data qubit is changed to minus 1 ket state. So you kind of assume that there must be a Z error occurred in between these two cycles. We don't know when. We don't really know when. It could be occurred here, it could be occurred here, but somehow in between this cycle, in this circuit, there was Z error on the data qubit. And then we take another cycle, let's say. So I'm not doing any logical operator. I'm just saying that just want to preserve the quantum state and see the same quantum state at the end. So in the second cycle, let's say our measurement outcome was just the same 1. So that means the minus 1 eigenstate is preserved from cycle 1 to cycle 2. So there's no Z error occurred here. So let's say I'm taking another one. So here 0, so into plus 1, and again, so we have 0, plus 1, and 5, and let's say we have changed to minus 1. So we can see that, okay, so there was that error right here when it changes the eigenstate. When it changes, so we know this by changing, see the measurement outcome here is changed here. And also there must be that error in this stage. So all that we know is this. So we record the measurement outcome as a bit. Each cycle is run by pre-designed quantum circuit. We don't know. We don't have any control of changing the circuit, but we're just taking the measurement outcome and record it. And then this is your result. Then how many times it changed the bits? 1, 2, 3. So that means 3 Z error should be occurred. So that means whatever you got at the final result has to be modified by multiplying or acting the Z gate at the end, because that must be the correct, supposedly the correct answer. So I'm hoping that you got understanding of this. So any questions about what really the quantum error correction is? This is the whole idea. We're not correcting it, we're detecting it, right? Based on our detection, we're gonna change our result. We're gonna modify our result according to it. So if there was no error, everything must be 0, right? Right? That's the best case scenario. But it's inevitable to have an error. So just measuring the measurement qubit and then do some modification at the end. Okay. So this is the error detection of 1 qubit, right? And and also just 1 qubit and it can only detect whether there was a Z error or X error just once, right? So we don't know what's going on in real. I mean, it could have an X error, but what happens when you have an X error? An X error doesn't change the eigenstate. So it was already an eigenstate of X gate. So having more X gate on this circuit, this register, does not change the eigenstate. So we cannot detect X error by this. So in order to find an X error, you have to use Z-measurement. So let me summarize this. So I'll give you another name. So we have measurement qubit, or sometimes called syndrome measurement. So there are two. The one is X measurement, like this one, and another one is Z measurement. And this one detects Z error, and this one detects X error. Any questions? So it's clear by looking at the final result that if you have Z error, you change the eigenstate, right? But this is kind of obvious result. Obvious because of this identity. That's what I was saying. Without actually going through all this computation, you could have just expected that, because it was originally +1 eigenstate of X gate, right? And having Z error or Z gate changes +1 eigenstate into -1 eigenstate of X. So now, since it was -1 eigenstate, it doesn't matter what the quantum state of measurement qubit was. After going through this circuit, the measurement outcome will be changed to 1. It will be always 1 if you have -1 eigenstate in your data qubit.